When you're looking to detach an electronic component from a circuit board or substitute one, make an effort not to leave the soldering iron resting on the component for an extended period. Because if that electronic component is still functional and you subject it to excessive heat, you'll ultimately cause it to fail and you'll be solely responsible for its damage, even though the component was fine. So make sure you perform the component removal as quickly as possible. Observe as I demonstrate. When you're working with either a desoldering pump or a soldering iron, you must operate very swiftly to ensure the component is not damaged. So, regarding the optocoupler's pins. Once we've melted and weakened the solder, we'll use tweezers on one side of the optocoupler. Very gently, without applying any pressure at all, we'll approach its pins. We'll hold it with the tweezers just like this, and then on this side, we will reapply a bit more heat to make it detach much more easily. If any tiny solder remains, it should detach easily. As you can see, it's coming off smoothly. It will be gently removed, with absolutely no pressure needed. Likewise, from this angle, we'll continue using the tweezers. Your tweezers also really need to be top-notch indeed. Tools are key. We'll steady the tweezers on this side and then gently remelt the solder on these pins a little bit more, ensuring it detaches effortlessly and without any struggle at all. Alright, we're going to carefully remove the optocoupler from the circuit board. It still requires a bit more heat until it fully detaches. So here is the optocoupler, which as you can observe was effortlessly removed from the circuit board. We'll carefully straighten its pins a little. If you remove the optocoupler properly, its pins won't even suffer any bending or distortion. We can see here that it hasn't become crooked or bent in any way. Now let's look at the method for testing an optocoupler. Although we covered how to test them in the last session, we're going to demonstrate the procedure practically right now. We put the multimeter in diode test mode like this, and then we'll also test its probes once to ensure functionality. We'll test it like this. Now let's test the optocoupler in this manner. You'll notice on one side, as you can observe, there's a small dot. This specific dot, when installing the component, must be precisely aligned with the corresponding mark that is located on the circuit board itself. Observe, if we direct our attention to the optocoupler's location, you will distinctly notice a specific mark present at this very point. Right here. See, this is where the optocoupler is installed. Where it's marked, you'll find a symbol on this particular side, clearly indicated. This optocoupler's dot should face that specific mark, and that's precisely how we'll proceed with its installation. But what is the testing method precisely? We will essentially place the multimeter's probes into diode test mode and then attach them to two of the optocoupler's pins. In this instance, I'm instructing you as if you're unfamiliar with identifying its input and output pins. Some optocouplers have marked input-output pins, others don't. In this scenario, you will observe that one of the pins from a certain side yields no input whatsoever. When performing the test in this manner, we will then reverse the orientation of the multimeter probes. Now we will connect the positive probe to this other pin of the optocoupler. This implies we check each pin in both orientations to verify the optocoupler's functionality and ascertain whether it is fully operational. We'll test it again, the optocoupler. Well, this specific pin doesn't register a reading in either direction, and it's likely the one connected to the transistor component. And once we've tested this particular side, we will proceed to test the other side as well. Again, in that same way, one time in one direction, then once more in the other. I will connect the multimeter probes to the optocoupler's pins, exactly as shown, and then proceed to test its other pin with the second probe. Following this, I will carefully reverse the directions to complete the test. Alright, as you can see, it provided us with a numerical value in a singular direction. Therefore, when a reading is displayed solely in one direction, it indicates that this specific side corresponds to the optocoupler's optical diode. Thus the photodiode pins. As mentioned, an optocoupler's one side is a photodiode, the other a light-activated transistor. As LEDs, LED lamps, and regular diodes pass current in only one direction, the optocoupler should show a reading on one side in one direction. Since this optocoupler showed a reading on one side in one direction, it means its diode side is working fine. And since the transistor doesn't connect its collector and emitter pins until it's powered on, thus preventing the necessary current from flowing, it's logical that these two pins should be completely disconnected in both directions. Given that these two pins are indeed disconnected, this clearly indicates that the optocoupler is fully functional and perfectly healthy, allowing us to confidently use it. Therefore, we can now proceed to reinstall the optocoupler, allowing it to remain securely in its designated position as it is fully functional. Alright, I'm now installing the optocoupler in its proper place. If you observe during this test that none of the optocoupler's pins are connected to each other, or if a pin related to the diode indicates a reading when measured in both directions. This means current is flowing bidirectionally when it ought not to be, indicating a faulty optocoupler that you should then proceed to test and ultimately replace. Alright, we'll now place the optocoupler exactly back in its original position. When you're installing it, pay close attention to ensure it sits precisely where it was before. However, before we proceed to install the optocoupler in its designated position, it is essential that we first prepare the pinholes by clearing out any old solder, a process similar to what we've done previously for other components. This ensures a clean and straightforward installation of the optocoupler. Therefore, we will now meticulously clear out the pinholes in this area. This way, I'll take off the excess solder so the pinholes are fully open and completely unobstructed, allowing us to effectively. We can comfortably seat the optocoupler right back into its initial position with great ease. Alright, that takes care of it. With great care and precision, we are going to accurately position the optocoupler exactly where it belongs. We'll proceed with its swift installation now. Alright, once we've installed the optocoupler in this manner, we'll proceed to carefully solder it into place from this side, ensuring a secure connection so that it's perfectly positioned and secured without issues. You must be extremely careful during soldering to ensure that. Therefore, do not apply too much heat to the optocoupler. As stated, if excessive heat is applied to any electronic component, it will quickly malfunction, even if it was initially functional. So, it's very important to pay attention not to apply too much heat and to do the soldering in the shortest time possible. And your soldering work must be exceptionally precise and clean, ensuring that the component's pins do not short circuit against each other. As you can observe, the optocoupler's pins have been soldered properly and securely here. You see, if I pull the plastic back just a little bit, you'll find it's soldered almost as good as new. Okay, we successfully positioned the optocoupler in its designated spot. Now I will proceed to install the fuse resistor, which I have specifically chosen for this purpose. It is advisable to use a high wattage resistor since it performs better. We'll install this resistor right here, then proceed to solder it into place. Proceeding in this manner, we will also carefully install the 2N60 transistor back into its designated and rightful original position on the board. Alright, I'm gently bending its pin a bit due to the component's arrangement on the PCB. Its pin must be bent slightly in this manner. Then I carefully position it in its proper place and proceed with the soldering process on this side of the component. Once I have completed the soldering process, I will proceed to trim the excess leads that protrude, as it's imperative that no superfluous lead material remains. These excess leads themselves can actually cause a short circuit, as the pins located here should never, under any circumstances, come into contact with the metal casing of the power supply unit. Thus, we proceed to completely trim away all the excess leads. Once we've properly trimmed the component leads, you will clearly observe the solder joint, which is perfectly secured and well connected. Now we will reinstall the capacitors, the heatsink, and all the components that we had previously taken out. After that, we'll plug in the power supply to check if the issue is resolved and if the standby voltage is present. Once we've installed the initial MOSFET transistor, be it a 2N60, a 6N60, or any other model, the specific part number isn't crucial for our purpose, and properly secured the resistor as well. Our next step will be to focus on this BJT transistor you see here before us. As mentioned, there is also a BJT transistor. We've tested the optocoupler and confirmed it's working, but the BJT transistor still remains. At this point, we need to test this BJT transistor as well, to see if it's good or not. So let's go to this side and remove this transistor from the board. And test it off the circuit board. We simply cannot determine the functionality of a transistor, whether it's good or faulty, while it remains on the circuit board. Therefore, it is absolutely essential to remove it from the board. We will then carefully desolder and extract the BJT transistor from the circuit board. Alright, after we've sufficiently weakened the solder, we'll now use tweezers right here. Just like how we removed the optocoupler, we grab the transistor. And with just a slight application of pressure, not excessively but a very minimal amount, we will try to carefully remove the transistor. It detaches quite easily, it just requires some patience. In electronics, rushing should be avoided at all costs. Okay, this is the transistor. Before we test it, we'll properly identify its pins and prepare them, because eventually we will need to reinstall this transistor, either this specific transistor or another one. Replace it with a different one, so the locations for the transistor pins have been prepared. Now we will test the BJT transistor itself. The method for testing a BJT transistor is indeed quite straightforward. We proceed by setting the multimeter to its diode test mode, and then we switch it on to commence the testing procedure. What we must do is this. Transistors, as previously stated, possess a base pin, A. They have a collector pin and an emitter pin. Leveraging the knowledge you've acquired, be it from Google searches or your previous hands-on experience, we'll start by identifying the transistor's pins to ascertain which is the collector, which is the emitter, and which is the base. Unlike MOSFET transistors, like the 2N60 we saw, these transistors don't have a gate, drain, and source. Their pins are called emitter, collector, and base, where the base pin is what turns the transistor on. The collector is the pin through which power enters the transistor, and the emitter is the pin through which power exits. Within transistors, the collector and emitter pins absolutely must not have any connection between them, or if a connection exists, it should only be unidirectional, or they should show extremely high ohmic resistance. And they should ideally exhibit a very straightforward and facile connection. This means that the collector and emitter pins should readily permit the flow of current only when the base pin detects or gets a signal or voltage. In the absence of a signal at the base pin, the transistor's collector and emitter pins should not have any conductive connection, meaning they should remain isolated from each other. As mentioned earlier, the transistor utilized within this power supply unit is a C945 type, easily identifiable here, and stands out as one of the most frequently employed transistors in the field. If we hold this transistor, you'll observe its backside possesses a distinctively curved semicircular form, contrasting sharply with its completely flat opposite side. It's quite evident. If the flat side is facing towards us, the first pin here becomes the emitter pin. If the flat side is facing us, then the middle pin is the collector pin, and the pin at the very end is the base pin. Alternatively, reading from right to left, the pins are base, collector, then emitter. So with this information, we proceed to test it. Alright. So what we need to do is, having identified the base pin, we then connect the red probe, which is the positive probe of the multimeter, directly to that base pin. In this manner, using the negative probe, we proceed to test both the collector and emitter pins. Upon doing so, we should observe a clear indication of current flow between them. I'll position the multimeter to make it more clearly visible for you. As you can observe, the multimeter indicates a current flow. This current is flowing from the collector pin and likewise from the emitter pin. Okay, we have no current flow on the emitter. Now, just because there's no current flow doesn't mean anything yet. This is because we will now reverse the probe connections. We will connect the multimeter's negative probe to the base pin this time, and then we will proceed to retest the emitter to ascertain whether there is indeed current flow or not. You can observe that current flow is indicated solely by the collector, whereas no current flow is registered at the emitter. I just want you to observe the testing procedure. So we've connected both probes, specifically both the positive and negative leads, to the base pin. In this particular scenario, it was only the collector that indicated any current flow or established a connection. Now, after we perform the test using the base, we will proceed to disconnect the base from the circuit. Then we proceed to test the collector and emitter terminals in conjunction to ascertain whether they establish an electrical pathway or not. You can see that in this situation, when we connect the probes in both directions, it doesn't allow current flow in one direction. We then switch the probes to their opposite positions, and this time, we test it once more and observe that there is no current passing through. This signifies that this transistor is also defective and has completely failed. So how can we determine this? As previously stated, the base pin should establish a connection with both the emitter and the collector, showing a reading in at least one direction. Furthermore, the collector and emitter pins should not exhibit any direct connection unless they receive a command from the base. However, as is evident, this particular transistor fails to adhere to any of these fundamental principles. Therefore, we will put this transistor aside for now, and then we'll get a new C945 transistor that is actually brand new. First, we will test it out for your observation, and subsequently we'll install it in the exact spot of the previous transistor. Alright, so we're going to put a new transistor right here, specifically the C945 model. We'll then proceed to test it to demonstrate how a properly functioning healthy transistor operates. Okay, at this point we will connect the positive probe directly to the base pin. Initially, with the negative probe again, you'll observe that the collector continues to display a reading. Well, the emitter on the other transistor didn't show any reading, but here you can observe that the emitter is now providing a reading. This means this transistor is healthy. Well, it's a different type of transistor. You saw the other transistor's pins didn't conduct at all, but this one's base conducts to both other pins. Meanwhile, the other two pins should ideally have no connection between them whatsoever, or at the very least, they shouldn't show a connection in a single direction. You can observe that the collector and emitter terminals remain isolated from each other, requiring a command from the base to establish any communication. Therefore, this transistor is indeed functional and in good condition, so we will proceed to substitute it for the previous transistor right here at this very spot. Okay. Now, how exactly do we install this transistor? And on the power board, how do we discern which side is the base and which are the emitter and collector? And in which orientation should we even mount the transistor? As previously mentioned, if you recall, the schematic is often printed directly on the board itself. Observe here, as the manner in which this transistor burned out is completely evident. You can see it has blackened the board. Since it has blackened the board, the Zener diodes here are also suspected of being faulty, so we must test them. However, prior to testing the Zener diode, I will present the schematic to you. Observe here, you'll notice the transistor, as previously mentioned, possesses a distinct form. You'll see a semicircular shape depicted in this image. This precise shape is also distinctly present on the power board itself. Observe, we can clearly see the semicircle right here on the board. This side is curved like a semicircle, and the opposing side is flat, so we position the transistor precisely as indicated by the shape on the board. But first, as previously stated, given that the Zener diode is also suspected of being defective, we will now test this Zener diode to confirm its proper function. As it's not possible to test it directly on the board, we'll, as usual, remove the Zener diode from the board so we can test it accurately. We must accurately locate its pins to prevent any potential errors or mistakes from occurring during the process. Here, I will precisely identify its pins and then proceed to carefully remove it from the board. Any component positioned closely to these transistors, having been affected by the incident and the resulting short circuit, could certainly be damaged and therefore absolutely requires replacement. We are going to proceed and meticulously detach this Zener diode too. Alright, after I've removed the Zener diode, it's the usual principle that applies. Initially, we'll prepare the fin holes for the Zener diode on the board. This preparation ensures that whether we're reattaching the very same diode or installing a brand new one, the pin holes will be all set, allowing us to easily substitute the component without any hassle. Alright, the pin positions are now prepared. Let's proceed to test the Zener diode itself. In order to perform the test on the Zener diode, it is essential that the multimeter remains set to its diode testing mode. And typically, the way you test a Zener diode is exactly the same as how you would test a standard diode. It should only have current flowing one direction, from the anode to the cathode. Therefore, we connect the positive probe, which is typically red, to the anode terminal of the diode. The Zener diode's cathode, as plainly seen in this image, is characterized by a distinctive black band around its side. This visual marker allows for easy identification, as you can readily observe its presence. This means it has a black line marking but not on the anode side. The marking is only on the cathode side. Therefore, we connect the black probe to the cathode side and the positive probe to the anode side. In this situation, you will observe current flowing, and the multimeter will display a reading. And now we'll reverse the probes. We'll connect the positive probe to the cathode and the negative probe to the anode. If it's working correctly, there should be no current flow. Okay, as you can see, the Zener diode is fine, thank goodness, no problems here. So we can simply place this diode back into its original position. When it comes to installing components, specifically for the Zener diode, we adhere to these exact same principles. This means you should pay attention to the marking on the board so you don't get the direction wrong. You see the diode installation direction is as follows. The anode and cathode sides are completely clear. You need to install the cathode side towards the arrowhead marking that is right here, which corresponds to the Zener diode, and then position it. Therefore, we will proceed to reinstall the Zener diode right back into its original position. Alright, after putting the Zener diode in place, we'll go ahead and do the soldering. Just like this. Once we've completed the soldering process, the subsequent task involves meticulously reinstalling all the components that we had previously taken out, and thereafter, we will proceed to power up the circuit board. Alright, moving on. We will now proceed with installing the transistor. As we still haven't installed our 3945 transistor, we'll carefully position it in its designated spot and subsequently solder it securely into place. After we have properly positioned the transistor, we will then proceed to carefully solder it into place. Once we finish soldering the transistor in place, we will then proceed to cut off the extra leads. This is due to the transistor being brand new and possessing extra leads. You absolutely must trim the excess leads and pay very close attention to this matter.
If you neglect to trim the leads, they could ultimately lead to a short circuit. This means they can come into contact with the board or the metallic body of the power supply, leading to a short circuit. The aim of faking this plastic sheet, as you can observe, is precisely to ensure that this section of the power supply remains distinctly separated from the main body of the board. This prevents any inadvertent contact between these delicate components and the board structure, thereby safeguarding against potential damage or electrical malfunction. Because when the board is broken, as you can see, there should be a gap created in this manner. Therefore, if you install a component and its lead is too long, it can cause a short and damage the power supply again. Alright, we're going to reinstall the components we've taken out. Specifically, the heatsink along with the transistor we previously removed will be returned to their original positions and then soldered securely into place. We'll then observe if this power supply board successfully powers up or if it continues to experience problems. We'll position it right here, and subsequently we'll proceed with the entire soldering process. When soldering, as previously stated, the key rule is to perform the work swiftly. Don't forget, you really want to prevent damage to the transistors or components. Since electronic components are delicate and should not be subjected to excessive heat, care must be taken. Alright, this transistor has been soldered as well, and you must pay attention, apart from the heat issue, to ensure that none of your solder joints make contact or create a short circuit with each other, and that your soldering work turns out to be very neat and tidy. Alright, once we've completed the soldering, we proceed to position the transistors and the heatsink back into their designated spots. Following that, it's now time to address the capacitors that we had previously taken out. When installing capacitors, always pay close attention to their direction. The capacitor's negative terminal must be oriented and positioned towards the colored side. So we will now proceed to meticulously install the capacitors in this manner. It's essential to install the capacitors, otherwise you'll inevitably encounter problems. We will install and solder the capacitors in place, focusing on one side first. Okay, the next capacitor. We'll put it in place and solder it. Alright, so we've finished up this part and all the components have been carefully reinstalled. The capacitors have also been installed, and now we're going to proceed to test the power supply once.